All right, welcome to a brief introduction to the nomenclature and structure of alkanes. These are some of the simplest organic compounds that we can describe in courses, but as we're about to find out, just alkanes can become so large and complex that they're really quite an amazingly diverse class of compounds. Let's get started. Let's begin with the four simplest normal alkanes. And we use the term normal to describe an alkane in which the carbons are all connected in a straight chain. Now the first four of these would consist first of methane at CH4, ethane at C2H6, propane C3H8, and butane C4H10. Now notice that each of these compounds has a molecular formula which can be represented as a more simple equation, CnH2n plus 2. This is going to be true for all of the alkanes that we're going to look at today. So the four simplest normal alkanes are methane, ethane, propane, and butane. Now, their names come from historical references to when and where and how these compounds were discovered, and that's a topic for another lecture. What's important to know is that once we get past 4 carbons in a chain, chemists seem to have come to their senses a little bit and started using a more systematic nomenclature system. For example, 5 carbons is a pentane, whereas 6 is a hexane, 7 is heptane, and so on. And it doesn't stop at 10 carbons either. The system continues for as many carbons as we can possibly imagine connected in a chain and then saturated with hydrogens. But the complexity of alkanes goes far, far beyond the compounds I've shown you so far. You see, there's no rule that says that all the carbons in a hydrocarbon must necessarily be connected in a straight chain. They can be branched. So let's take the example of hydrocarbons consisting of 4, 5, 6, and 7 carbons and see how many different ways we can connect those carbon atoms in branched patterns. 4 carbons gives us 2 potential isomers, whereas 5 carbons can be connected in 3 different ways. 6 carbons gives us 5 possibilities, and 7 carbons gives us even more, a total of 9 different potential geometries. So these structural isomers, as you can see, the number of structural isomers that could be formed as a function of the number of carbons in the hydrocarbon is growing extremely rapidly. And if we continue to extend our list onward to 8 carbons, 9 carbons, and beyond, what we find is that there are a tremendous number of these structural isomers that can form. If we run some numbers here and take a look at how many different structural isomers we can make, given a certain number of carbons, the expansion of the number of possibilities is really quite dramatic. By the time we reach 8 carbons, familiarly known as octane, there are 17 different ways to connect those carbon atoms. If we go even further, to 16 carbons, we have a molecule called cetane, which is commonly found in diesel fuels. That has over 10,000 different possible arrangements. And we don't have to go much farther before we reach millions of possibilities. So with all these different possible connectivities and structural isomers with as few as 21 different carbon atoms combined, we've got to come up with a very systematic way of naming them. Because I can tell you this much, I don't want to have to memorize over 1 million different names simply to describe hydrocarbons to my colleagues. So I have to use a different type of system, something which is broken down into just a few simple rules which will allow me to characterize these millions of different compounds in an unambiguous way. Enter the International Union of Pure and Applied Chemistry, known as IUPAC, a standards organization which makes recommendations to chemists on how to name compounds, among many other things. Let's try applying the systematic rules proposed by IUPAC to name this molecule, which would commonly be called isohexane. Now, to begin constructing the IUPAC name, I find the longest continuous carbon chain in the molecule. In this case, the longest continuous chain is here. I have a total of 5 carbons in the chain. Now notice I could just as easily have used this chain as the longest, and it wouldn't have changed the geometric arrangement of anything. So I can take my pick in this case, and I'm going to choose the one that's easiest to look at, that goes left to right across the screen. So even though this molecule has 6 total carbons, it's going to be called a pentane, because the longest continuous chain of carbons within the molecule only has 5 carbons. My next task is to name all of the branching substituents which are not a part of the parent hydrocarbon chain. And I name them using a standard prefix, just like I did with my normal alkanes, meth, eth, prop, etc. But I end them in a YL suffix. This lets the reader know that I'm talking about a substituent. So in our example here, I have a single substituent which has 1 carbon. So this would be called a methyl substituent. Next, I have to number the parent chain in such a way that I can get an address to tell my reader exactly where that methyl substituent is attached. So I have to start from one end of the chain and work my way across to the other. And I choose a direction which gives my substituent or substituents the lowest possible numbers. For example, in this case, I have one direction of numbering giving me methyl at the 2 position, and my other option places the methyl at the 4 position. Because my first numbering scheme gives the methyl group a lower numbered address, that's the one I'll be using. Now I'm ready to construct my name. To name the compound, I simply take my substituents in alphabetical order and I preface them with their address on the parent hydrocarbon, finally naming the parent hydrocarbon. For example, this compound is a 2-methyl pentane. I now have a very systematic and unambiguous way to name this hydrocarbon consisting of 6 carbons. Let's try another one. How about this compound? Well, here I have a hexane, 6 carbons long, which has an ethyl substituent and a methyl substituent. Now I need to give the addresses to my substituents. I'm going to number it in such a way that I have a 2,4 substituted compound. If I went the other way, naturally I would have a 3,5, and that's going to give me higher numbers. So I would call this a 4-ethyl 2-methyl hexane molecule. Let's do one more. How about this one? Now you might be tempted to look at this molecule and say to yourself, well, there's a carbon chain running left to right, and that has 6. But this is actually not a hexane. We have to consider the fact that there's a longer chain. Even though it's not drawn straight across the screen left to right, it still counts as the longest carbon chain. So this is actually a heptane molecule. Now my heptane molecule has 4 substituents, each of which has a single carbon, meaning I have 4 methyl substituents. So when I number my chain, I need to do so in a way that gives my methyl substituents the lowest possible number, and then I name my compound. This is going to be a 2,3,4,5 tetramethylheptane molecule.
Hey everybody, it's Professor Davis here from ChemSurvival.com and the YouTube channel ChemSurvival, and I hope you just enjoyed the video you watched on alkanes, their nomenclature and their structure. And if you'd like to learn more, I'd encourage you to learn more about my new DVD course coming out in October 2014 from the Great Courses. You can find more information at www.chemsurvival.com. And in the meantime, don't forget to subscribe, share, and like as many videos as you please. The more we get the word out, the more everybody's going to learn this semester. I look forward to being part of that. See you on the next video.